Good evening all. I'm Tausif Anwar, and here we are for the live session and problem solving session for the course Welding of Advanced High Strength Steels for Automotive Applications. So right now we are in the 4th week of this course, and 3 live sessions we have already covered. So where we saw about different types of automotive steels and whatever welding, what are the welding processes that we utilize to weld them. And then we are right now into the welding metallurgy of this advanced high strength steels for automotive application. So today it's 4th week live session, and the date is 16th of September 2022. So yeah. So in this week we started with the sequence of microstructure formation. If you are doing a weld, then it will have basically mainly 3 zones. That is fusion zone, and then heat affected zone, and then parent metal. So in the fusion zone, metal will be melting, and after welding, that melt will be solidifying. So if it is solidifying, then what are the sequence of microstructure that it will be going through, that we saw. And then depending on the alloying element, that sequence of microstructure may vary, and also the width of this heat affected zone, that also depends. We saw that on the welding processes. Then when we saw that effect of in trip steel and in DP steel, we know the microstructure, but after welding, how do we quantify, how do we know that this much amount of let's say austenite or retained austenite is there in the heat affected zone, or whatever is the microstructure we are getting in the fusion zone or heat affected zone, how do we quantify? So that also we saw, there are different methods to quantify. So we saw that, and among that we discuss in detail that mainly 2 methods. The first one was vibrating sample magnetometry, where we based on the magnetic property of the different phases, we used to quantify it. And then we saw that XRD, X-ray diffraction technique, which gives the phase fraction, and from there we can quantify. So that X-ray diffraction is not the normal one. It is basically a synchrotron based XRD, which works in a transmission mode. So it can transmit through the sample, and it can give the data of the phase fraction of the different phases. And at last we saw that effect of alloying element and the effect of weld cycle on the property of our weldment. For example, we took a normal carbon phosphorus containing steel, and then we increased the carbon content, and then again we added boron into it. So then we saw that effect, and then at the end we saw that let's say if you don't want to add the alloying element, you have a normal this automotive steel containing carbon and phosphorus, and you want to get a good weld using spot welding. So in that case, we saw that if we alter that weld thermal cycle by engineering the way we supply the current, and the way we apply the force in case of spot welding. For example, in one case, in the conventional spot welding process, we give a forge force, and then we apply the pulse, single pulse. So then we get some property. In other case, what we can do is we can increase the duration of force applied, and then we give instead of giving 1 pulse, we can give 2 pulse after the first one. And then we saw that the microstructure, and we studied the property. So that's all. That was all about from the week 4 content. Now we will move to the problem solving, some sample problem from the content of week 4. So the first question is there on your screen, which says, which of the following microstructural constituents in the steels is or are paramagnetic at room temperature? So the options are ferrite, option B is martensite, option C is austenite, option D is non-metallic inclusions. So out of these four options, you have to select the paramagnetic, or you can say non-magnetic constituents in the steel. So just read the question and options and then try to answer it. So among the ferrite, martensite, or austenite and non-metallic inclusions, so you have to identify the non-magnetic phase. So you can type your answer in the chat box, or else you can unmute and tell your answer. Both are fine. So I will first of all explain. When we use this automotive steel, so they are like mainly ferritic, or the main phases that which are present here is ferrite, can be ferrite, pearlite, cementite, martensite, austenite, and non-metallic inclusions, right? Non-metallic inclusions. So whatever is the microstructure, so as I told earlier, that we use a test called VSM, that is vibrating sample magnetometry. So actually it works, the main principle behind that is it identifies that ferromagnetic element, and based on the percentage of ferromagnetic element, the saturation magnetization will vary, and if it contains paramagnetic element or non-magnetic element, that saturation magnetization will decrease. So that's how we identify the presence of non-magnetic elements. So among these four, austenite and non-metallic inclusion, these two options are correct. That is, austenite and non-metallic inclusions are paramagnetic element. So let's say if you have a structure which is 100% ferritic, so in that case ferritic or ferrite plus some amount of martensite. So let's say that P versus H curve will look like this, and your saturation magnetization value is let's say it is up to here. So in other case, let's say you have this is 100%, let's say ferritic microstructure. In another case, let's say you have some amount of ferrite plus retained austenite. So what will happen in the second case, that saturation magnetization value will be decreased. So this will be the saturation magnetization in case of the microstructure containing retained austenite. So this is how this VSM will identify the presence of non-magnetic elements. So the right answer for this the option question number 1 is austenite and non-metallic inclusions. Now I request you to read the question number 2 and tell the correct answer. So this is question number 2, which you can read on your screen. The question 2 is compared to HSLA steel with same carbon concentration, the saturation magnetization of tripped steel is. So just now I have explained what will happen if your microstructural constituents differ from one to another. What will happen to the saturation magnetization? So if it is HSLA and then in another case it is tripped steel, then what will happen? The saturation magnetization will be higher or low, or same as B can change only if the carbon concentration is changed. And the last is same as the temperature below the Curie temperature. So just read the options and then tell your correct answer. So as I told, this tripped steel compared to HSLA steel contain retained austenite, right? And that this retained austenite is basically paramagnetic in nature, paramagnetic or non-magnetic. So when your microstructure contain retained austenite, then the overall this magnetic saturation magnetization value will be decreased. So as you can see here, the case 1 and case 2. So let's say this case 1 is of HSLA steel, right, and then in case 2 it is of tripped steel. So since tripped steel contains the retained austenite in its microstructure, then the saturation magnetization will be lower than that of tripped steel, HSLA steel. So this is of HSLA and this is of tripped steel. So the right answer is low, always low. Compared to HSLA steel with the same carbon concentration, the saturation magnetization of tripped steel is always low due to the presence of retained austenite in its microstructure. Good. Now we will go to the next question, question number 3. So you can read the question on your screen. The question is, the width of heat affected zone HZ in welded tripped steel is in general larger than conventional steels because of. So here it is asking in tripped steel the width of HZ is wider compared to the conventional steel because of perlite formation, oxidation during welding, or decomposition of retained austenite, or vaporization. So you have to select the right option. So as I told, the microstructure of tripped steel is nothing but ferrite plus bainite plus retained austenite. So this bainite is nothing but PCC structure only, which is rich in carbon. So now you have to tell why it is wider in case of tripped steel. Hello, am I audible? Ayush? Am I audible, Ayush?
Yes, sir.
Huh. So I think you have joined just now. So for your information, I will just tell what we are doing right now. So we are solving some sample problems, and based on the content of week 4. So whatever content is there in week 4, so based on that we are solving some sample problems. So already we have solved 2 problems, and now we are solving the problem number 3rd. So I request you to please read question number 3rd, and based on your understanding just answer it. Don't worry whether it's correct or not. We'll try to understand that. Is it clear, Ayush?
Yes, sir.
Yeah. So I request you to please read the question number 3rd and try to comment your answer, or you can unmute and tell your answer. And then we'll try to understand the concept behind it.
Yes, sir. Yes.
Yeah, sure. So the question is, width of heat affected zone in welded strip steels is in general larger than conventional steels because of what? So that you have to identify. So as you know, the strip steel microstructure consists ferrite plus bainite plus some amount of retained austenite. So this is the microstructure of strip steel. Now think about this problem. So let me explain the concept behind it. So in the lecture itself, sir has shown this graph, which shows basically it's a kind of silicon based strip steel, strip steel. So in this case, as you can see clearly, there are 2 graphs. So the first one is temperature, which is shown here in yellow. I'm highlighting it by yellow color, and the second one you can see is the austenite fraction with respect to the as you move far away from the weld center line towards the parent metal. So let's say this is your weld. So this is your weld, and this is your based on the composition, this is the HSZ, heat affected zone, and this is your parent metal, and this is nothing but this entire zone is fusion zone, and the center line is called weld center line. So as we move from the weld center line, the temperature, as you can see, decreases, and the magnitude or the steepness, or the you can say the slope of this temperature depends on the type of welding process that you use. And this is how the temperature cycle look like. And now coming to the phase fraction, that is percentage austenite, that is retained austenite. So as you move towards the fusion zone, so let's say we are moving from the base metal towards the fusion zone, so what happens is your amount of retained austenite decreases, and this decrease is basically nothing but it is due to the conversion of this retained austenite into the ferrite plus carbides. So depending on the time that you provide, so it can be like ferrite plus epsilon carbide, then this carbide will be converting to ferrite plus nita carbide, and then at the end this will goes to ferrite plus theta, that is Fe3C. So these are this is how the transformation of retained austenite into the more stable phases, that is ferrite plus cementite, takes place. And as you can see, this transformation, during this transformation the amount of retained austenite is decreasing. So this is what happens during the transformation, or as you move towards the weld center line, and you can see again that retained austenite amount is increasing, and this happens due to the temperature goes into the intercritical region, and then again it decreases, and this happens due to the temperature vent where we don't have any retained austenite, and then in the fusion zone it is almost maintained at some constant value. So as you can see, from the weld center line till the noticeable change in microstructure. So here let's say up to 12 mm we see there is a change in microstructure from the parent base metal microstructure, which is ferrite plus bainite plus retained austenite. After the 12 or 13 mm we can see the noticeable change in the heat affected zone. That is what the definition of heat affected zone is. Wherever you see a noticeable change from the fusion zone towards the base metal, the entire that width is called heat affected zone. So as you can see here, the width of heat affected zone is almost 12 mm, and this happens due to this the presence of retained austenite, or you can see and this retained austenite basically transform to various like ferrite plus different types of cementite or carbide. So the main reason behind the larger width of heat affected zone in trip steel is basically due to the decomposition of retained austenite, and that decomposition is nothing but retained austenite is converting into ferrite plus epsilon carbide, and then again it is converting into ferrite plus nita carbide, and then again it is ferrite plus theta, that is Fe3C cementite. So during this transformation that magnetic property will be improving, and that this width of this will be causing the wider width of heat affected zone. So the right answer is option 3. Now we'll go to the question number 4, which says, while welding dual phase steel at the heat affected zone where the peak temperature reached is below the AR1 temperature, then what will be happening? Option 1 is grain refinement takes place. Option B, martensite can get tempered. Option C, cementite gets dissolved into the ferrite, and then martensite lathe refinement takes place. So for your knowledge, I will just clarify what is AR1 temperature. So this R we use when we are cooling from higher temperature. So let's say the carbon, like low carbon region of iron carbon phase diagram. So we have that is eutectoid region, where we have here complete austenite, and then here we have ferrite plus cementite, that is theta, and this is theta, this is alpha, and this is alpha plus gamma. So this region, this temperature, we call it as A1 temperature, and when we are coming from higher to lower temperature during cooling, and then this temperature is called AR1 temperature. So in this problem it is asking if you are heating while welding DP steel at the HSZ where the peak temperature reaches below AR1 temperature. So now the peak temperature reaches below AR1. So let's say this is a weld thermal cycle at HSZ. So the peak temperature reaches like this. So it is near to the AR1. So what will happen to the microstructure? So whether it will refine the grain, or martensite will temper, or cementite get dissolved, and martensite lathe refinement will take place. So that you have to tell. So for your hint, I will tell the microstructure of dual phase, which is nothing but ferrite plus martensite, right? So this alpha prime is nothing but martensite and this alpha is ferrite. So now if you are heating this microstructure or during cooling, the temperature reaches around like below the AR1 temperature, then what will happen to the microstructure? That you have to tell. So as you can see, we have just now seen the example of retain austenite. So similar to that, some the phenomena will happen, that is decomposition of earlier we saw the decomposition of retain austenite. So here what will happen, instead of retain austenite, what we have martensite. So what will happen, this martensite will decompose into the further stable phases when you heat near to the AR1 or A1 temperature. So this martensite will get tempered basically. So it will give ferrite plus carbide, that is epsilon carbide, then this ferrite plus neta carbide, then again it will transform to ferrite plus theta, that is cementite. So this phenomena is nothing but the tempering of martensite. So the right answer for this problem is martensite can get tempered. So option B is the correct answer for this problem. I hope it's clear to you. Now we will move to the next question, that is question number 4th. Question number 5th. So you can see here, double pulsing resistance spot welding weld thermocycle improves the mechanical properties of the weld by. So if you use double pulsing resistance spot welding, then what will happen to the mechanical properties? So it will changing the primary weld nugget size, like it's going to change the weld primary nugget size, or homogenizing the elemental segregation, or expulsion, or keyhole formation. So you have to choose the right option for this. Just think a little bit and then tell your answer, and then we'll discuss the concept behind it and then answer for this problem. So in the conventional welding, resistance spot welding, what we do is we apply a force. Slowly we apply a force, we maintain it for some duration, and then we unload it. And when the force reaches to a like certain value, during that time what we do is we apply a current, right, like this, for a very short duration. But here in double pulsing, what we do is, instead of using a single pulse, what we do, we will increase the force application duration and we will use 2 pulse, or you can see double pulse. So the first pulse we can give here like this, and the second pulse can be given in this way. So this is what we do is in double pulsing resistance spot welding. So you have to tell, if we move from this to this, what will happen to the mechanical property. So we will see the effect here. So just now I showed you that what is the difference between the cycle, that current or force versus time cycle. in conventional single pulsing and double pulsing. So here you can see that pulses are repeated like twice, and the effect is shown in this slide. Addition of second pulse significantly improved the cross tension strength and failure mode of resistance spot welded 1 GPa third generation advanced high strength steel. So you can see in single pulse the cross tension strength is approximately 2 kilonewton, and when you use double pulse it goes till let's say 3.8 or 3.9 kilonewton. So yeah, obviously this single to double transition or use of double pulse will increase your cross tension strength. Coming to the failure mode, in terms of plug ratio, which is nothing but the ratio of diameter of plug to the weld nugget size. This is diameter of plug after test, and then this is the initial plug size, weld nugget size. So you can see this failure, this plug ratio is all improved when you change it to double pulsing. So from almost 50% plug ratio to more than 80% plug ratio we are able to achieve. So combination of modeling technique validated by experiments shows that the improved mechanical behavior. So mechanical properties basically getting improved is linked to why it is getting improved is linked to a reduction of phosphorus segregation at the solidification grain boundaries. So basically the phosphorus segregation is getting minimized, and your microstructure is getting homogenized, and due to that homogenization your mechanical property is getting improved. So in terms of elemental segregation, that segregation is getting homogenized, and due to this homogenization of elements like silicon, phosphorus or sulfur, the mechanical property is getting improved. So the right answer for this problem is homogenizing elemental segregation. So double pulsing will homogenize the elemental segregation. So the option B is the correct one. Now we will move to the next problem, question number 6. So softening of fusion boundary in aluminum containing tripped steel is due to the stabilization of what? So I showed you the graph of silicon containing tripped steel earlier, which is like this. Similar to this, that graph of aluminum containing tripped steel is there. So where the softening of HZ will be observed. So what is the reason for that softening? Softening of not HZ, sorry, it is asking softening of fusion boundaries in aluminum containing tripped steel due to the stabilization of what? So what phase in aluminum containing tripped steel got stabilized, which causes the softening in the microstructure? So think a little bit and then try to answer. So for your hint, I have given the microstructure and the sequence of microstructure that will form when you cool it from liquid phase. So think a little bit and then try to comment your answer in the chat box. So somebody is saying option B, that is oxide inclusion. Okay, now we'll see what is the correct answer, and we'll try to understand the concept. So you can see here when we cool it from liquid region, so the first phase which will be forming is a delta ferrite, right? And then as you decrease the temperature, that delta ferrite plus that cementite. So cementite from delta ferrite to cementite, this austenite transformation will start, and delta ferrite plus austenite will be there, and after crossing this line, we will be having complete austenite. But before the formation of delta ferrite itself, you can see there is a this darker dots, which are nothing but oxide inclusions. So which will be forming at a very high temperature itself. So here you can see it is approximately some 1800 degrees Celsius. So based on whether it's silicon containing tip steel or aluminum containing tip steel, so whatever is there, so aluminum oxide Al2O3 and silicon oxide SiO2 will be forming first in the liquid itself, then delta ferrite, then austenite, and then lower temperature phases will be forming. So the first phase, which will be first thing which will be forming here, is the oxide inclusions. But it is asking about softening of fusion boundary. So in case of aluminum containing tip steel, what happens is when the fusion zone gets solidified, so the partitioning will be happening. So the aluminum is the only element which partitions towards the solid. Usually what happens, the element will try to partition into the liquid because of its more solubility in the liquid than that of solid. But in aluminum, the reverse will be happening. So the aluminum in the fusion zone will be try to diffuse into the delta ferrite which is forming. So here you can see the delta ferrite. This is nothing but delta ferrite. So the aluminum will be diffused from the fusion zone, and the delta ferrite will be formed at the fusion boundary, and this is our HZ. So in the fusion zone, whatever this microstructure will be having, that is ferrite plus bainite plus retained austenite, right? And here it is delta ferrite. So delta ferrite is a basically soft phase. So at one side, let's say in HZ, you have phases like of retained austenite, and in other side you have delta ferrite. So due to that, stress partitioning will be happening, and this softer phase may be later on be possible that the failure may be happening here in the softer region. So the softening of fusion boundary in aluminum containing tip steel is due to the stabilization of delta ferrite by the aluminum. So this aluminum basically stabilizes the delta ferrite, and it doesn't allow delta ferrite to transform to austenite, which is a higher strength phase, and the softer phase remain as it is, and due to that the softening of fusion boundary occurs. So the right answer for this sixth problem is option A, delta ferrite. So I hope it is clear. Now we will move to next problem, question number 7. So I request you to please read the question number 7. Hello Mohan, I think you have joined just now.
Sir, a little busy.
Yeah,
So
it's fine. So what we are doing is similar to what we did in last week. So we are
okay, sir.
now at problem number 7. For remaining
No
six
problems. Like
remaining 6 problem we have already solved, and then it is recorded, so you can refer it in the in your SWAYAM portal. Recording will be
okay, sir.
uploaded. Yeah, so you can refer.
Okay, sir.
From now you can read the problem and answer. So the 7th problem is the fusion zone of DP steel's primary comprises of. So first of all, for your hint, this DP steel microstructure is nothing but if you take a DP steel, then the microstructure will be ferrite plus martensite. Now if you are doing welding with this microstructure, then we will be having this is our weld bead, let's say, and then here till here, let's say it is heat affected zone, and then after that it is parent metal. So this fusion zone where we did this welding. So what will be the primary microstructure? So what will happen to this phase if you do welding? That you have to tell. So in fusion zone, the temperature goes more than the melting point. So whatever microstructure you have, it will vanish. The liquid will be there, and then from liquid to the other phases, the transformation will be taking place. So in the problem, it is asking about the primarily, like just think a little bit and then tell your answer. So in DP steel, if you observe the fusion zone microstructure, so it will be mostly ferrite. So the right answer is ferrite. Depending on the cooling rate, you can have this a little bit of martensite also, but primarily the microstructure will be consisting of ferrite. So the right answer is option B. Just a minute, somebody is calling. Let me pick call. I will be back. Hello, hello. I'm in class now. Class. Okay. Half an hour I will. After half an hour I will come and collect. Yeah. Sorry for the inconvenience. Now we will try to solve question number 8. The primary nucleation sites for acicular ferrites. So if your acicular ferrite is forming, then what will be the nucleating site for it? Fusion boundaries, ferritic grain boundaries, or martensitic lathe boundaries, or non-metallic inclusions. So for your hint, in the earlier problem here, I have shown the sequence of the microstructural constituents formation. So I will repeat it again. What happens is when you have a liquid steel, like if you are in the liquid phase region and you have started cooling it, so the first thing which will form is your oxide inclusion. So based on the type of element you have, if you have aluminum, then aluminum oxide Al2O3 will be forming, silicon, then SiO2 will be forming, and then upon that this ferrite will be nucleating. So the first thing which will form, you can see here the temperature is approximately 1800 and you are cooling it. So as soon as we started cooling, the first thing which is forming is this black dots, and these black dots are nothing but oxide inclusions, and on that oxide inclusions only that ferrite will be nucleating. So you can see here from A to B, here this final product, if you see, and these are nothing but ferrite, and the morphology of this ferrite is acicular. So we call it as a acicular ferrite. So this is what it is asked in this problem. So the primary nucleation site for acicular ferrite is nothing but non-metallic inclusion. Yeah. The option D is the correct one. I hope it is clear. Now we will move to next question. Question number 9. Try to read. Which one of the following element is R known to minimize the phosphorus segregation at the weld center line? So boron, manganese, rare earth elements, or hydrogen. So among these, if you use that element, so it will minimize the phosphorus segregation at the weld center line. If you know, then you can comment your answer. Option A, B, C, D, or else. So I'll tell the right answer. So when you add boron, then what it does is it will minimize the phosphorus segregation at the weld center line. So it is in the lecture itself, sir has taken some example of a steel, like steel containing carbon and phosphorus, steel containing twice the amount of carbon and the same amount of phosphorus, and the third case, steel containing carbon, phosphorus, and boron. So these three cases sir has taken, and then the observation was this phosphorus. When you add phosphorus, so when you add boron, so it minimizes the phosphorus segregation at the weld center line. So let's say this is your weld nugget, and this is a weld center line. So this is nothing but your spot weld. I'm taking it as a spot weld example. So usually if you don't have boron, so the last liquid which will be solidifying will be containing high amount of phosphorus, and if you do a tensile test, so like this, then through this crack will be propagating due to the segregation of the phosphorus. So it was not assumed to be it is not observed to be good to have a phosphorus segregation at the weld center line. So then what we do is we added the boron, and the presence of boron in the weld microstructure minimizes this phosphorus segregation. So the right answer is boron. If you add, it will minimize the phosphorus segregation. Now read the question number 10 and try to answer it. Which one of the following element diffuses out of the liquid to solid during solidification of strip steel? So usually what happens, you have solid and liquid, so the element will try to diffuse from that alloying element will try to diffuse from solid to liquid in most of the cases, but here it is asking which one of the following element diffuses out of liquid to solid. That is reverse, it is asking from liquid to solid, it is asking in the strip steel. So it's a kind of exception only, and due to this we get poor mechanical property. So whether it's carbon, phosphorus, sulfur, or aluminum, which element partition from liquid to solid, that you have to tell. So yeah, so the right answer is aluminum, correct. So this aluminum basically partition from liquid to solid, and that solid is nothing but delta ferrite. So in the earlier problem itself, I told you this microstructure. If you see the microstructure of this aluminum containing strip steel, it contains this region, this white containing region. This region is nothing but delta ferrite. So the aluminum will partition from this solid to liquid, and which stabilizes the delta ferrite, and later on it may act as a softened region which will deteriorate the mechanical property. So the right answer is aluminum, correct. Now problem number 11. When the retained austenite fraction increases, the saturation magnetization of strip steel. So what will happen to saturation magnetization? It will decrease or not change, or increase exponentially. So if you plot the curve between B versus H, so the plot will have a look like this. Now let's say in one case we have say X% of retained austenite. In another case, let's say we have like case 1 we have X% of retained austenite. In case 2, let's say we have X plus delta X % of retained austenite, and these two are the curves. So in one case saturation magnetization is this B saturation, and this is B saturation 2. This is 2, or you can say saturation A, saturation bar, and saturation. So in what will happen to this? Which one will be suited for this? Either first will go there, or first will follow this second one. Yeah. So as you know, this retained austenite is nothing but our paramagnetic phase, that is non-magnetic phase. So when you increase the amount of retained austenite in your microstructure, then it will obviously decrease the saturation magnetization. And this is what the principle of magnetometry is, which uses the amount of retained austenite in your microstructure to calculate the phase fraction. So that curve 1 is for this, and case 2 is for this. Now we will move to problem number 12. Softening of heat affected zone in dual phase steel is due to sterilization of perlite, tempering of martensite, formation of martensite, or retained austenite. So what is the reason of HSH softening in dual phase steel? So for your reference, I have given you the hardness versus distance graph for dual phase steel. This graph is for DP steel, and we have used two different welding process, that is plasma arc welding in one case, which is denoted by this, and the second case laser beam welding. So you can see the hardness is getting decreased in the heat affected zone. So this decrease in hardness is due to what? In heat affected zone in case of dual phase steel. And dual phase steel contains ferrite plus martensite. This is the microstructure of dual phase steel. Ferrite plus martensite. Yeah, Mohan, what do you think? So retained austenite you are telling this here you can see there is nothing, no phase is there. Retained austenite is not there. Retained austenite is there in strip steel, right? Strip steel contains ferrite plus bainite plus retained austenite. But in dual phase steel we have only ferrite plus martensite. We don't have any retained austenite. So what happens here is this martensite, similar to the austenite, what will happen? Retained austenite, this martensite will get tempered. So the martensite will transform to what? Ferrite plus epsilon carbide, and then further it will transform to ferrite plus neta carbide, or we can say it E prime, and then it will transform to ferrite plus theta, which is cementite Fe3C. So this phenomena is nothing but tempering. The martensite is getting converted into ferrite plus carbide, so, and due to that the softening is happening, because the martensite is the hardest one among these, and this is getting decomposed. So the tempering of martensite is basically responsible for softening of HSA. Yeah, good. Now we will move to few more problems. Problem number 13 of this session. In aluminum containing advanced high strength steels, which metallurgical reaction occurs first when the weld pool is formed? Delta ferrite stabilization, formation of oxide inclusions, acicular ferrite formation, austenite formation. So already I have explained this, just you have to see the option and tell your answer. When you cool it from liquid region, the first phase or first thing which will form is what you have tell in case of aluminum containing tip steel. Yeah, mom. What do you think? Acicular ferrite formation, that is not true. The first thing which will be forming is the formation of oxide inclusion. First of all, the oxide will form. Let's say here it is aluminum, then Al2O3 will form. This oxide, let's say this is our liquid melt. First of all, oxide inclusion will form. Upon that, the ferrite will form. Ferrite will be forming. So this is our ferrite, and this ferrite will form on the inclusion. As you can see, the first thing will form is inclusion. So if you go back to this cooling curve, the first thing here in liquid which is forming is, you can see, inclusion. These are the inclusion, oxide inclusion. So the oxide inclusion in aluminum containing steel is Al2O3. So the first Al2O3 will form, then delta ferrite to austenite, austenite to complete austenite, then lower ferrites. But you can see the end product is acicular ferrite, and this acicular ferrite is forming on the inclusion itself. So the first nucleation will be of oxide. So I hope it is clear. I will show you this. So the primary reaction which will be forming, let's say this aluminum containing tip steel with a little bit of silicon oxide also. So the first thing, the core you can see here is aluminum oxide. Primary reaction is aluminum oxide formation. Upon that, silicon oxide will be forming, and then if some impurities like manganese sulfur is there, then manganese sulfide will be forming, and then so on. But the primary reaction here is Al2O3, that is oxide inclusion, aluminum oxide. So the right answer is option B. I hope it is clear, Mohan.
Yes, sir.
Yeah. Now we'll solve the 14th problem. Delta ferrite gets stabilized in fusion and grain boundaries in trip steels weld by silicon enrichment, carbon enrichment, aluminum enrichment, manganese enrichment. So already you told earlier, the stabilization of delta ferrite in trip steel is by aluminum, right? From liquid and solid, aluminum will partition from liquid to solid, that reverse case, and that solid is nothing but delta ferrite. So this delta ferrite stabilization is by aluminum. So this already we have explained. So that's what we have for this session. Thank you so much for joining the live session. If you have any doubt, you can and this is the last.
I need to go through again.
This remaining question you can refer. It will be recorded and it will be uploaded there in the SWAM portal. You know where it is? Recording is getting uploaded.
Okay, sir.
Do you know that the recording where we use?
Yes, sir.
Okay. So any doubt in previous lectures, like week 1, week 2, week 3? or any issues, because this is the last live session we are having, and directly after this the course is completed and you will be going to write the exam. So have you registered for the exam, Mohan?
Yes, sir.
Okay. So if you have a doubt, you can ask now, or else we have a Google forum also. So in your SWAYAM portal, one tab is there where you can click and ask your doubt. So that also you can utilize.
Okay.
Yeah. So later on, if you feel any difficulty, you can write to us, and we'll be happy to answer that. Thank you so much for joining this session. Thank you. Yeah. Okay. Thank you.